When we talk about ice tables are something that can help us with equilibrium calculations. That is, it really just sort of simplifies and lays out all of the calculations that we have to perform using equilibrium concentrations. So ice table stands for a different set of concentrations at different points throughout an equilibrium system. So the I refers to the initial concentration, and when we're dealing with concentration, we're talking about molar concentrations. Incidentally, the ice table can also be set up for amounts in terms of moles or partial pressures, but we're just going to take a look at it in terms of its molar concentration. The C refers to a change in concentration, and the E, of course, refers to the equilibrium concentrations. So let's take a look at how we actually use this by taking a look at an example. So here we have an equilibrium system between gases, three gases. We have two reactant gases and one product gas. So we have hydrogen gas and iodine gas forming hydrogen iodide in an equilibrium with that. We can see that there are 2 moles on the reactant side and there are 2 moles on the product side. So if we set this up in terms of our ice table, we can see that we have our initial concentrations. Typically, we are going to find scenarios where the product is going to have an initial concentration of 0, because most of the time what we're doing is we're putting in the reactants first and then allowing the equilibrium system to establish itself at equilibrium. So initially, typically, we have initial concentrations of the reactants and we have a 0 concentration or no concentration of the products. And then, of course, we have to think about the change in concentration. And really, that's most of the time what we're trying to figure out. So what is the change in concentration going to be? And so in most cases, we're dealing with a decrease in the concentration of the reactants and an increase in the concentration of products. And if you remember the mole ratio, we would say that 1 mole of hydrogen reacts with 1 mole of iodine to produce 2 moles of hydrogen iodide. So for every mole of hydrogen or for every mole of iodine that the reactants decrease, you're going to see an increase in 2 moles of the product in this case because of the coefficients from the balanced chemical equation. So it's really important when you're taking a look at the change in concentration that you know the balanced chemical equation and that it's correct, because it's going to affect the change in the concentration of your reactants and your products, because the coefficient matters. And then finally, E is just a sum of the I and the C. So the initial plus the change in concentration, and that's what it gives you there. And then ultimately, you just plug those values into the Kc expression, given whatever information that you have from that particular question, and you solve for the variable that you're looking for. So given your Kc, then you can just plug in those variables. Again, it's products over reactants. Don't forget that the coefficients also count when you're putting together your Kc or your equilibrium expression. So don't forget to square it or cube it or raise it to the power of whatever exponent represents that particular compound. So really what we're looking at is just the setup for these types of problems. I'm not going to go through a specific example, but what I want you to do is remember this format as you go through examples on your own. So based on the question, I want you to be able to evaluate it and set it up, format it like this, and then we can take a look at analyzing those responses. But there are a few things that I want you to be aware of when you go through these types of questions that'll make your life a little easier. The first thing is, if you find that you have a really high initial concentration and a really low Kc value, what that means typically is that you can negate the change in the concentration, because the Kc value is going to be so favored to the reactants that the change in concentration is going to be really minimal. So if the initial concentration over the Kc, and this is just a bit of a test that we do, is greater than 500, you can negate the change in the concentration. That is, you don't have to worry about the value of X if the concentration, the initial concentration, is greater than 0. If the initial concentration is 0, for example, for a product in most of our reactions, if the initial concentration is 0, then any change is significant, and so you don't have to negate it. If the denominator and the numerator are both squared, or they're both cubed, most of the times it's going to be squared, you can take the square root of both sides, that is the Kc itself and the values in the Kc expression, and that's going to make things a little easier on yourself, because what you're going to find is that if you have a lot of exponents, in your particular Kc expression that you're solving for, if you're solving for x, or the change in the concentration, which is probably what you're going to be doing most of the time, you may have to use the quadratic equation from time to solve for the value of x. And if you take a couple of these shortcuts, it's going to make it a lot easier on you, and you're going to reduce the number of times that you have to do complex calculations, like using the quadratic equation. Another thing is that state is important. Concentration is really dealing with the amount of something per unit volume. But if we're dealing with liquids or solids, these are substances that are more or less in natural states, and they have specific or fixed concentrations, or their concentrations don't really impact the Kc value as much, or they're even considered within that Kc value. So state is important. Only gases and aqueous solutions have concentration, and since the Kc or any equilibrium expression is involved or deals with concentration, if that particular substance doesn't have a concentration that's going to change by any measurable effect, that is, it's a solid or a liquid, we don't include it in our equilibrium expression. And then finally, you have to understand and know which way this direction is going to shift. And you can use the reaction quotient, for example, to help you out with this, but you have to understand whether the reactant concentration is going to go up or is going to go down. And that's going to impact whether or not your change, or your C in the ice table, is going to be positive or negative. So what I want you to do now is take a look at the way that I've set up this ice table, take a look at an example problem, and see if you can work your way through it. Keep in mind some of these tips because they might make those calculations a lot easier. Thanks for watching.